Hi everyone, this is Ashley Bedford, founder of the Runtime Diaries, and I'm super excited for this day 26 problem on our hashtag 30 Days of Code challenge with Educative. Today we have valid anagram. Let's get into it.
Today, we're looking at one of the simplest LeetCode problems on the surface, but underneath it, it teaches 3 foundational patterns you'll use again and again: sorting, hash maps, and counting arrays. And if you want to dominate string problems later, from group anagrams to minimum window substring, this is where the foundation really starts. Let's break down valid anagram. The problem is extremely straightforward. Given 2 strings, S and T, return true if T is an anagram of S. Otherwise, return false. And in case you need a refresher, an anagram simply means same characters, in any order, with the exact same frequencies. So it's not about the order at all, it's purely about counts. Let's see a couple of examples. Anagram and Nagram return true. They use the same exact letters in different order. Rat and car return false. They have different characters, so they're definitely not an anagram. This is easy to understand in plain English, but our job is to turn that intuition into efficient code. I know this problem seems tiny, but it shows up everywhere. This one idea, comparing character frequencies, is the backbone of group anagrams. Permutation in string, find all anagrams in a string, character replacement, minimum window substring, sliding window logic, and even rolling hash algorithms. This simple challenge is actually a training exercise for much bigger concepts. The most natural first instinct is to sort both strings and compare them. If the sorted versions match, they're anagrams. If not, they're not. This works, but it costs O of n log n time because sorting isn't free. So we can do much better. To truly optimize, we need to rethink the approach. We don't care about the order of characters. We only care about the frequency. So the improved idea is count how many times each character appears in S. Subtract how many times each character appears in T. And if all counts return to 0, the strings match exactly. This lets us solve the entire problem in O of n time. Before counting anything, we can make a very quick check. If the 2 strings have different lengths, they can't be anagrams, period. So we return false immediately. This is a tiny optimization, but it eliminates a lot of unnecessary work in real test cases. The fastest and cleanest way to solve this problem uses a 26 length counting array because the problem uses lowercase English letters. We can map each character to an index using ord of our character minus ord of the character A. Then loop once over S and increment counts. Loop once over T and decrement counts. At the end, if the array is all zeros, we know the strings match perfectly. It's compact, fast, and uses constant space. Here's the full Python solution. We start with an early exit on length mismatch. We create a counting array of size 26. For each character in S, we increment the corresponding index in the count array. For each character in T, we decrement the corresponding index. If any count goes negative, we return false immediately as an early exit. Finally, we check if any values in the count array are 0. If they are, we return true. This is the most optimized form of the problem, and the pattern shows up everywhere later. Let's break down the complexity. The time is O of n. 1 pass to count, 1 pass to subtract, and 1 pass to verify. Or we exit early if we detect a mismatch. The space is O of 1. We only ever use a fixed array of 26 integers, which does not scale with input size. That's as optimized as it gets. There are a few other approaches that you may see. First, sorting. You can use sorted of S equals sorted of T. Very intuitive, but it's O of n log n time. Second, you can use a counter from the collections module. You can use counter of string S equals counter of string T. It's still O of n time and very readable, but it uses a heavier data structure. Third, bit mask. Some people try bit manipulation, but it doesn't work here because bit masks can't store frequency. They collapse duplicates, so strings like AABB fail. The counting array remains the best choice for this specific problem. Let's do a walkthrough. S equals A, B, B, C, A, and T equals B, A, C, A, B. When we count, S bumps up the frequency array. Then T subtracts each frequency. The final array ends up all zeros, and that's how we confirm it's an anagram. This frequency counting pattern is everywhere. Once you understand this deeply, problems that used to feel overwhelming suddenly become mechanical. Sliding windows, checking permutations, matching substrings, keeping balanced character counts, maintaining windows in linear time. This is one of those small building blocks that unlocks huge progress later. Let's recap. First, anagram means same character frequencies. Second, counting array solves in O of n time. Third, early exits improve efficiency. Fourth, sorting is valid but slower. And fifth, this forms the foundation for dozens of advanced problems. This is one of the cleanest examples where simple ideas build real skill.
And that's a wrap for day 26 of our hashtag 30 Days of Code Challenge with Educative. If you like this video, like it down below, share it with a friend, and subscribe to our YouTube channel. We hope to see you again. Bye!